Hi, so my name is Oleg Maslov. I'm working as a software engineer for Intel company. So I want to thank you for bringing me here. So I'm going to give a talk about validation of OpenCL compiler. Okay, so I was told to put the stage right from the beginning, so I'm going to do it now. So the problem which I'm going to talk about, that we have a, let's suppose we have a complex system. So software system, it contains a lot of components, and we needed to validate it somehow. So suppose we have a set of tests, but these are system tests. They test the whole entity, this whole system. And for early development of the single component, for example, for enabling new architecture, you need to ramp up quite quickly. So you need to develop each component in parallel. And there needs to be some kind of mechanism which enables to validate each component, to do basically component testing individually. So that's when the place when we apply the LLVM interpreter. Okay, so the stage has been done. Let's move next. So the agenda for today, that I'm going to say a few words about OpenCL standard language itself, what it is, and our solution coming from Intel for OpenCL implementation. Then I'm going to tell a few words about validation tool, which we implemented for validating OpenCL compiler. And then I'm talk about interpreter, changes we made to this because we had to make some changes, and the contribution we're going to submit to community. Okay, so few words about standard. So basically OpenCL is just about heterogeneous computing. So there is a possibility to, it provides a possibility to program either GPU or CPU. So it's kind of an open standard language, so it's maintained by Khronos group. So any vendor can take the standard and implement its own OpenCL implementation for this. So it's cross-platform and it's relatively free. So the language itself, what it is, it's basically inherited from general C99, but there were an additions of vector operations. There were an addition of multiple built-ins. There is some limitation like recursion. You cannot do a recursion there. So it has a unique execution model like configurable and dimensional execution, when you can invoke one-dimensional, two-dimensional, and stuff like that. And there are various special functions. So this stuff allows you to program quite good. What's wrong? Sorry. Okay, excuse me. So this stuff allows you to program either CPU or GPU. So, okay, about this is a kind of a slide which product we make. So we support the full stack of core architecture. So we provide 1.2 implementation for our CPU for internal graphics, and also there is coming soon a support of OpenCL for Xeon 5. It's kind of new architecture. It's multi-core architecture. This is a card. So please feel free to download, to go and take a try to use these products. Okay, so now let's move to the standalone tool. So I should mention that I will cover here the details of implementation for CPU and for MIC architecture. Xeon 5 is the same, so I'm not covering here graphics. So the typical application looks like this, so which uses OpenCL. So it interacts with the OpenCL implementation using API, and the system OpenCL comprises of a lot of components. These are runtime, basically, which handles the API calls, the front-end compiler, so it's Clang-based, which produces LLVM IRA. So OpenCL device backend, which is LLVM-based, and basically it it outputs a JIT code to be executed on the device, either on CPU on Xeon 5. So it's a big library of built-in functions supporting OpenCL, And there is a device runtime agent which runs actually JIT code, and the parallelization which is used to parallelize multiple threads running the code on the device. So the message here is that the system is quite complex. So it contains a lot of components, and the task of validating each component is quite challenging. So the Khronos itself provides us with a so-called conformance tests. These conformance tests, it's a system-level tests. So they test the system of OpenCL implementation as the whole entity. So, and it does not allow you to test each component. So you need to have all components ready to run the conformance tests. So let's talk a bit how we started implementing, supporting a Xeon Phi MIC architecture. So that was a pretty challenge because of the card itself. So let's talk a few about the card. So it's an add-on card. So this is the processor. It has 64 cores, as far as I remember. So, and very wide SIMDs unit. So it's 512 bits register. So when we started working on this project, so everything was not ready. So all the components of the system were just ramping up and starting development. So by that time, I myself was working for backend team, which produces, so JIT produces. So we needed to enable early validation as possible to start developing our component there. So we needed somehow to invent how to validate the backend. For doing this, let's consider the data flow of code in our compiler. So first we use front end, which is Clang based. It takes as input OpenCL kernel, then it produces LLVM IR. So, and then we have we call it device backend. This is the system comprising of several blocks. So the first one is we apply a set of standard LLVM optimizations. Then we have an OpenCL specific passes like vectorizer, inter-work item optimization and stuff like that. Then we import built-in functions library. And after that, we have a code generation, which actually produces the JIT code. Okay, so we needed to validate this device LLVM device backend. The idea is pretty straightforward. So we just isolate this component from others. So what we do next? So then we implement so-called standalone tool, which basically uses the interface of this device backend to perform compilation of the kernel. And then there is a block which allows you to execute the generated JIT code. So that's how we can isolate it, compilation and running the produced JIT code of the LLVM device backend. The next thing that we needed to compare it against something. So for doing that, we implemented the so-called OpenCL reference. That's where the interpreter comes into play, LLVM. So for obtaining reference results, we used LLVM Interpreter, and also we implemented a block with a set of library of reference functions, which are slow, but they produce highly accurate and stable results running those built-in functions. Okay, so those reference and device backend shares the same interface, so standalone utility can talk to them in a similar way. Okay, then we compiled from OpenCL LLVM IR for compiled from OpenCL and the data. So LLVM IR is being recorded from real-life applications, so there is a special model for doing this. So we record this IR and record data and put it as an input to standalone utility. Okay, so after that, when we have results of running JIT code and results of running reference, we have a module called Coprocessor. So it compares basically outputs, results of running JIT code and results of running on the same kernel and data reference. So this is pretty straightforward. So not that pretty straightforward, but okay. So but it manages to give you an output does it output buffers are equal or no. So this is a kind of a how it performs. Okay. So this standalone utility also has a, not also, so it has a 3 modes, basic modes of operations, which we implemented. First, that was a functional validation. So basically, it functionally checks the device backend. So it runs it on some captured LLVM kernel and it's on the data. And basically, it makes makes sure that it's compliant with OpenCL 1.2 standard, since we have a reference engine which is supposed to be compliant. So it was run on real-life kernels and data captured from them. The second mode we also use in very quite useful for us. It's a performance mode of the utility. So basically, it measures compile time and it measures kernel execution time. So this is quite useful because we want to isolate those components from others. For example, if you have a performance regression with a system, so if you see that if you have those kernel recorded and you can run through the standalone system, so you can see if the performance degrades there and if this is really relevant to backend, or it comes, or if not, it may come from some other components of the OpenCL ecosystem. So execution is done in single thread mode, so that's to simplify and to isolate the backend. And the third mode, this is a kind of a debug and a develop mode, so it's build mode. So during this in this mode, developer can dump the code of IR, dump the code assembly, and directly it allows developer to track and debug optimization. So we use this tool for our LLVM device backend developers. Okay, now let's talk a bit what we changed in Interpreter. Interpreter itself, it was a must-have component for reference. So what it basically does, so it takes out input directly from Clang. So we made sure that it wasn't, no optimization were applied. So it's kind of a pure output. It can be used as a reference. So Interpreter itself, it's pretty straightforward. It just takes instruction one by one and executes them. So the benefit here is that it produces quite accurate results. So the disadvantage of this is that it's quite slow. When we took this version of Interpreter from LLVM trunk, we found out that there is a missing support of any vector and aggregate types. So there were no instructions supported doing those vector operations or aggregate type operations. So we needed to implement them. So this is a typical example of OpenCL kernel and LLVM IR produced from this. So kernel on the left, it just simply computes exponent on the input buffer and output it's to the output buffer. So the instructions shown in red, these were not supported in Interpreter when we started doing this. So these are multiple memory access and store operations, calling and other stuff. So that was the instructions that we needed to add support. So now a bit technical detail how we implemented this. So the interpreter logic is put into the class interpreter, so it features kind of several important fields. So one of this is EC stack. This is basically called stack of functions. So it stores a vector of execution context when the function calls stack. The essential methods for interpreter class is run function, which invokes running function f with arguments, and multiple visit handlers. So basically those functions handles different LLVM operations like load, store, and stuff like that. So we needed to get there. So, and execution context itself, it represents a basic block which is being executed, its function, next instruction, and also it stores a context of running function. So these are arguments, and these are local variables. So the generic value basically is this structure is used to store the values itself, variable. So initially it looked like this. So it has a union, which basically has a can contain double, float, pointers, etc., and integer values. So there were no choices of vector and aggregate operations. So what we did here is just simply we added the single field. We called it aggregate val. So this is a standard vector referring to the same generic value. So adding this single field enable us to support vector and structs and arrays because so basically in case of vector you can resize aggregate val and it will store the elements of equal type. In case of structure, so the situation is the same. You just has a number of elements in vector which is the same as the number in struct. So, but each element can be of arbitrary type. So adding this field, basically that's the sense of the work. So adding this field allowed us to add the support of those types. So how we're gonna handle this? Let's take a look at typical visit operation. So this is like, for example, how the visit binary operation is implemented. So it basically checks the types of instruction arguments, and then it depending on type, so it performs execution. So in case of vector addition, we just place another case on vector. Then we have an instruction which resizes to the same number of vectors as an input, and then also the same ifs, which handles a floating point and integer types, etc. So this should give you an idea how it happens. Okay, so when we implemented this, so we had to add we added support of different types of operations, basically from LLVM. So we added vector memory access addressing, like load, stores, binary operations, in vector shuffles, comparison, bitwise conversions, etc., and also for supporting aggregate instructions. That's what we implemented for LLVM Interpreter. Okay, so now let's talk about another part of reference. So this is a library of built-in functions. So there are plenty of them, and we had to implement all of them using a high precision. So for example, just to obtain a maximum precision, we used to computate float. We use a double type to compute floating point output. For computing doubles, we use a long double. And so we implemented all of those functions. Now we think they are compliant with 1.2 standard, so we can use them as a reference library of built-ins. Now let's have a short demo. I'll basically show how this utility works, so in validation mode. So, for example, suppose we have a bug in compiler. So, we have some kind of kernel on which we're going to run this standalone utility. So, now I'm going to show how it detects and what's the process. So, the kernel itself, it's pretty simple. So it just calls a pop count built-in on the inputs and outputs to the destination pointer. Pop count built-in, basically it's a built-in which counts number of bits. Okay, so for running this test, we have a configuration file in XML format, which basically tells you which program file it uses. So this is program file type is CL type, so it means that it should be precompiled by Clang. And then it says that there is a kernel called the test name of the kernel and a bunch of runtime parameters coming from OpenCL. I mean, this is a work dimension, staff log worker size, global work size, etc. so it doesn't matter in this case. Okay, so we go to the command line, and that's it. So we invoke this utility. So the standalone utility, it says that it is being run in validation mode, and a configuration file used is popcount CFG. So the force ref flag means that we forces to generate reference. Otherwise, it will try to preload the pre-generated reference from the file. Okay, so when we run this, we see that there is a failure. So it reports, basically it reports the failure in buffer 1. So this is a destination buffer, and type of the buffer is vector. So, and there is a difference produced in the first value of the buffer. So in this case, the reference produces 3, and the actual, this is coming from backend, this produces 1. That's why there is a comparison, return the error. Okay, this is the sign that something goes wrong. So suppose we found out the root cause of the bug, and suppose I just, for simplicity, use that this is for example, we just will be modifying just directly LLVM-IR. So this is a library of built-in function, and this is a kind of an implementation of popcount built-in. Okay, and so actually in real life this is being compiled from OpenCL, but for simplicity, just like take a look at LLVM-IR. So for example, we find out that there is a typo, and there is a, instead of 2, there should be 1. So, okay, we change this value to correct as we think. Then we go back to the command line. So now we invoke LLVM assembly utility to compile to RTL. And voila, so now we invoke again standalone utility with the same parameters, and we see that the test has passed. So basically, in this example, that means that we have fixed the bug. Okay, now let's get back to the presentation. So, few words how it helped us when we developed a Xeon Phi. So basically, this tool enabled us to validate those green blocks while other blocks were not ready, so showing in gray. So, and we were able to start working on this compiler as early as possible. So even we managed to obtain some first results when the hardware was not ready. So we only had a simulator. It was functional simulator emulating those devices. So that was a great benefit for us, and we managed to start developing quite early. It saved a lot of time for us. So that's how it was useful for us. Okay, now a few words about what we're going to contribute back to community. So since we're it, so these are again the list of what we changed in the interpreter. So we added vector types and all types of operations which handles those vector types. So we're going to submit it to community. So we are we have committed already 2 patches. So basically adding a vector support and adding a limited set of operations. We are going to perform several incremental commits. So they're underway. And as a result, there will be we hope there will be vectors and aggregate type full support and interpreter. So you guys can use it. What is on our wish list? So we didn't implement a standard LLVM intrinsic support. So you should understand that we implemented all of the stuff which is relevant for OpenCL. I'm not sure that we will be fully compliant, but what mattered for OpenCL we implemented. So we enhance, and also constant expression might be helpful. Okay, so then summarizing, so the work, so we had initially we had multiple components developed simultaneously of the system, and we had existing system level tests which tested the whole entity. So we managed to have a validation using LLVM Interpreter. for our OpenCL implementation. That's all from my side. Thank you.
So, any questions? Actually, I have a question. So, in your adding support for aggregate values to the interpreter, I mean, do you support aggregates with nested aggregates?
Yes.
Okay, so you didn't show a recursive implementation on your slide, but that was just a simplification.
Yeah, it was just for simplification reasons. So you're welcome to see a commit actually.
I saw the patch.
I suppose just a quick question. One of the features of OpenCL is the barriers, and you didn't really mention whether you found LLR useful for debugging barrier kind of code. Did you have any techniques for doing that?
I mean, how we dealt with barrier function?
Yes, did you find any way of helping to validate that barriers are working correctly using LLI?
We were not able to use LLI since our backend has a special interface. So using LLI was not possible. So that's why we implemented standalone tool.
Right, but with your tool, did you manage to help debug barriers?
Yes, so we added the support of barriers. So since the execution is pretty sequential, so when you run the barrier, you just need to stop to detect barrier and to switch to another work item and run, etc., after all completed. So it was not of a problem for us.
Any other questions?
So my question is about the built-in you use. I would like to know how do they differ from the reference in the Khronos conformance test? The OpenCL built-ins you have implemented.
So it's a good question. So partially we looked at the Khronos implementation, ESML. So we used their implementation as a reference partially, but we used also our own internal developments. So since there is a good reference library coming maybe from internal like Intel compilers, so they have also those kind of libraries.
Okay, thank you.
Any further questions? All right, in that case, let's thank Oleg again.
Thank you. Thank you.